Hi, hello everyone, welcome back to the channel. So today we'll be solving a new problem, that is count the number of complete components. So in this question we have given the n and the edges. So what this n is, n represents the number of nodes present in the graph. So if we have given 6, so it means that we'll be given 6 nodes from 0 to n minus 1. Okay, so as you can see, it has started from 0 and we have total of 6 edges. Okay, this is the nodes and talking about the edges. So we have given one more thing, that is edges. So this 0 to 1 represents that we have an edge from 0 to 1. Then 0 to 2 represent we have an edge from 0 to 2. Same thing, 1 comma 2 represents we have an edge from 1 to 2. Okay, and again 3 to 4 represent we have an edge for from 3 to 4. Okay, so this is the information that we have given. So what the question is asking, so we have to return the number of complete components. So what is a complete component? So the complete component is that for each nodes in a component, suppose we have three components here, right? Because they are not connected to each other. So these two are connected to each other. That's why it is one component. These are connected to each other. Second component, and this is connected to none. So it is again a component because it is an alone component. Okay, so this way we have three components. Now, to make this component complete, we have one condition. So the condition is that for each node, it should have an edge for all the other nodes. For example, we have three nodes in here, right? So for this node, it should have an edge to all the other nodes. For example, this node and this node. So we have an edge from 0 to 1 and 0 to 2, right? And the same way, this 2 should have an edge to this 2, right? And this one should have an edge to this 0 and this 2. Okay, so this is what a complete component is. So let's take this example. So we have two nodes. So for these two nodes, it should have only one, right? Because they are connected to each other only. Let's take this example. Okay, so if this is, we have another two components, right? So now to check if they are connected components, so we have to check that, okay, if this 0 is connected to other nodes, so we can check that, okay, so for this one, it should connect to all the other nodes. So this is connected to all the other nodes. So this is a valid one. Okay. Now check for this one. So is 5 connected to 3? Okay, but this 5 is not connected to this 4. So that's why this is not an complete component. Okay, that's why we have the result as 1. And if you'll see in this case, the result would be 1, 2, 3. So this would be 3. Okay. I hope you have understood the question. So there is one thing that you must have observed, that okay, so for each component we have to check that, okay, it should connect to every other element, right? So suppose for this zeroth element, so for this zeroth element, it should connect with, it has connected with 1 and 2. Okay. For this one, it has connected to 2 and 0. Okay. And this, the last thing would be 2, that is connected to 0 and 1. Okay. So that's why it is a complete, because we have three edges, sorry, not, yeah, three edges, or we can say three nodes, right? So each node should connect to at least two other nodes. It means that for this component, we have component count, I'll say CC, is number of nodes are 3, right? So it should at least have n minus 1 other vertices. Is that true? Let's check. Okay. So for this, we have n is equals to 2, so that would be 2 minus 1. It should have at least one indices, sorry, vertex. Okay, so let's check that. Okay, 3 has how many? It has 4. Okay, and the same thing, 4 has 3. So if we'll check that, okay, the condition was that it should at least have one edge. So is it having one edge? Yes, it is having. Okay, so that's why it is a valid one. This is also a valid one. Let's check for this one also. So the n is 1, right? So n minus 1 would be 0. So we have 0 edges. Yes, we have 0 edges because it's just a single node. Okay, let's take this example. Okay, so we don't have any edge from 5 to 4. Okay, so now check, we have 3 nodes. So that would be 3 minus 1. That would give us 2. Okay, so it means that every node should have at least 2 nodes. So let's check. So this 5 have how many outgoing nodes or the edges? It has only one, that is 3, right? The same way, 3, it has 2, 5 comma 4, but this 4 has only one, that is 3, right? So now check, we have to get at least 2 nodes, right? But we have only one node here. We have 2 nodes here, but for this one we have also one node. So this won't be the valid condition. Okay, so I hope you understood the a bit of an intuition that okay. So to check the components, we have to check that okay, all the values should be equal to n minus 1. Okay, we can say that okay, for the length of what are graph nodes, right? Suppose let's take this 5. So this 5 would have the adjacency matrix as this. Okay, so these are what, these are adjacency matrix. Okay, the length of it, this matrix, I'll simply right now take, let's take G, right? It should be equal to n minus 1. If that's the case, we can take the component, right? Because this is the complete component. Otherwise, we won't take that component, right? I hope this problem statement and a bit of intuition is clear to you. So now let's dive deep into the intuition part. Okay, so this was the overall thing for the component one. So I hope you have got a bit of an idea on how to what to do now. Okay, so the first thing is that when I read this question, so there were a couple of things in my mind. Okay, so what we have to do, we have to iterate through this n, right? This is the basic thing that okay, we have to get this n's because we don't know that if this is connected or not. So we have to take all the values from 0 to n minus 1. Okay, now what we have to do, we have to get each component. Okay, so there are a couple of traversals. You can use DFS or BFS. I'll be using BFS. So you can use DFS also. That will also give you the similar thing because we just have to traverse or iterate through our graph. So we'll just simply use any of the algorithm. So I used BFS. So to get the component, we just simply have to do what? We have to add the values. So for example, whenever we'll traverse this one, we will simply add it in our component. So our component would have the value as this one 0, right? Because we have traversed that. And after we will traverse 1, then we will traverse 2. Okay. So this is how we will get the component through BFS. Okay. And after that, we will check that okay, if that component is complete or not. If that is complete, we are simply gonna add it. Otherwise, we're gonna ignore it. Okay. So this is the intuition part. So the component part, we have already noticed that, okay, what we have to do to check that, we have to check these conditions. What are these conditions? These are So this component will get all the nodes, right? 0, 1, 2, or 3, 4, right? For this one, it will get 3, 4. So this component, when we will traverse our BFS through BFS, it will store our value to 0, 1, 2. After that, we will simply check for these values. Suppose for this 0, we will check that, okay, for this 0, we will check our adjacency matrix that, okay, what is the length of it? So our adjacency matrix has length 2, right? And what is the value of n here? That is 3. N would be 3 minus n minus 1. That would be 2. So we have to check that, okay, is it equal to n minus 1? It means that is it equal to 3? Sorry, 3 minus 1. That would be equal to 2. Okay. So we'll check that, okay, is it equal to 2? Yes, it is. Its length equal to 2? Yes, it is. Its length equal to 2? Yes, it is. Okay. So it means that this component will be a valid one, right? Let's take the example of this one. So we will iterate using BFS. So we will get a value as 5, 3, and 4. Okay. These three values. So in this question, we have 5, 3, and 4. So in the component, we will get these values in our array. Using BFS, we will store that. I'll show you the code for that. And for the BFS and how to iterate that, I will upload the video for that. Otherwise, this video would be very lengthy. I don't want that. So I will add a separate video for that. So that way you can understand briefly and clearly how the BFS or the DFS works. I'll upload the video for both of the traversals, BFS and DFS. So that way it will be very clear to you. But I'll also show you the code for that BFS. So and also explain that. So I hope you will understand that. So now coming back to the question. So okay. So we'll check that, okay. For each component, we will check this 5. So we will check the adjacency matrix. What is the value of n here? So our component length is 3. So we have to take n minus 1. That would give us 2. So we have to check that, okay, is 2 available here or not? Let's see. So what is the length? The length is 1, which is not equal to 2. So as soon as we get any value that is not equal to 2, which is failing, so we will just get out of the loop or return false. Why? Because we can't take this component because this is not complete. Okay. Because on the first step we get that value that, okay, it is not complete, so we won't take this value. Right. So I hope you have understood the intuition part of it and also some of the hints and stuff. And I will highly recommend you to try and write the code. So I'll just give you the hint that, okay, what we have to do, 3 steps. We have to iterate through our n array and this one, okay. And after that, we have to create an adjacency list the same way that I have created, right? So for 0, we will check that, okay, the 0 will store the value in a dictionary. So 0 will have the value 1 and the 1 will have the value as 0 also. Okay, because this is not a directed, this is an undirected graph. So 1 is connected to 2 and 2 is also connected to 1. Okay, so the same way we will do the vice versa thing. And the same thing 0 to 2. So 0 then comma we will add 2 here and for 2 we will add 0. Okay. So for 1 comma 2 we will have 1 add 2, for 2 add 1. Okay. I hope you are understanding that. For 3 4 3 goes to 4 and 4 goes to 3 and 3 goes to 5, but we already have 3, so we'll add here and this would be 5. What can be the code for this? Really simple. So this would be the code for it. So we will iterate through the edges, right? Let's move it somewhere here, right? So for each edges, we will iterate that, okay, so it's graph u, the key. So not the key, actually the first one will append the value to v. So 0 will append to 1 and the 1 will append to u. Okay, so 1 will append to 0. So that way you will iterate and create the adjacency matrix. Okay, this is how you will create the adjacency matrix. Okay, now coming to the next part. So for the next part, we have to iterate through our BFS. So how to iterate through BFS? So I have this code here. So I'll explain you how this is working. So in the BFS, we will iterate through each element, right? So this is the component that I was talking about. We will create a component, this one component, okay? Then after that, we have this queue in which we will store our values. Suppose if we are starting with this one, 0, it will go to 1, it will store it in the queue, then it will go to 2, it will store it in the queue because after that it will take this one value and do the things, and after that, because 2 was in the queue, so it will start with this one also. Okay, so I won't be explaining you in detail how this BFS is working. I'll just simply uh, give you the summary of that. Okay, so we have taken this visited array because we don't want to iterate recursively all the time, so that's why we have this visited array. Okay, so it's like if we have visited 0, so we are not gonna visit 0 again, right? So this is what this is doing. So after that, we will store it in the queue. So in the queue, we will have this current element. After that, we will take this element and store it in our component. So this element would be suppose 0. So this 0 will, after that, we will append 0 here. Okay, in the component. After that, this 0 will get into the neighbors. So what are the neighbors of 0? So we will check our matrix, adjacency matrix. So this one, that neighbors of 0 are 1 comma 2. So 1 comma 2 would be this and this. So we will store it in our queue. As you can see, we are storing it in our queue, right? Queue dot append. So there's one more condition that, okay, if it is not visited, then only we are appending. If it's visited, then it's like we have done that, so we will not be doing that again. Okay, so that's why we are saying that, okay, we have visited this one, so please don't visit it again. Okay, so this is how we will traverse, and after the end of it, the while loop will end. So at that time, we would have traversed all the elements that are connected. Okay, so after that, we will simply return the component. So this is the result that we will get, these values. Okay, the components that we are talking about, these, we will get these values. Okay, now this is the second step done. Okay, now coming to the third step. So now for the third part, we got the value of components. Okay, so if you remember that, we have to check that, okay, if the length of the if the length of the adjacency matrix or the elements it is connected is equal to the number of components we have. So suppose we have the value of components. So I'll show you the code. Okay, so this is how we will compare that. Okay, we will traverse through our components. So these components we will traverse and we will check that, okay, we will check for this 5. So we are checking for this 5, this one. We are checking for this 5 graph node. So this would be 5. Length of this. So what is this length of this? So this graph 5 will give us the list. So this is the list. It will give 3. Okay. For now we have only 3, only one element. So if we will check for the graph value of 3, this one, we will get the value as 2. So that's why we are checking the length of it. Okay. So this is what it is doing. It is checking the length of it, right? It is checking the length of it. Okay. And after that, we are checking that, okay, if it is not equal to the length of the component minus 1. If you remember the n minus 1 that we were talking about, this is the n minus 1. Okay. So the length of the component means it will be Cn. Okay. So that you won't be confused with the n edges or the n nodes, right? That way. So the component's length is 3, right? So it will give us the component length. So we will check that, okay, if that's the case, if it is not equal, so what we have to do? We have to just return false, right? As we discussed. So now we will simply return false. That, okay, this is not a complete component. So we will break out of it. Okay. And we will check that, okay, if that was a complete component, if it was, we will increase the value of our complete components. Otherwise, we would do nothing. Okay. So this is the coding and intuition part of it. So I'll just simply write the code. This would all be the same thing, but I will simply write the code so that you can follow along. Okay. There will be three things as we discussed. So the first thing would be iterate through this n. Okay. So this n will iterate through it. Okay. Iterate. What is the next part? Use BFS. Okay. The last part, check complete components. Okay. So these are the three steps that we were taking. Okay. Now, first, we will write this BFS function. Okay. So I'll move it up and write this BFS function. Okay. Suppose I have written this BFS function, right? And one more thing we forgot, that we have to create an adjacency matrix. Okay. Not matrix accessory, adjacency list. I forgot. Sorry for that. Adjacency list we will do. Okay. So we are going to iterate through so that would be the vertex in range n. Okay. So that way it will give us all the values from 0 to n minus 1. Okay. So that way all the components are covered. After that, what this BFS will return us, if you remember, this will return us the components. Component. Okay. So the component we will get from this BFS. So suppose we get this BFS component. Okay. So for this node, we will return the vertex. Okay. So we will give the vertex that, okay, so this is the starting vertex. Now give me the components that are connected with, or the nodes that are connected with this component. So it will go here, okay, 0. It will say, okay, I will give you 0, 1, 2. So this will give us the list of components. Okay. Now, okay. So these functions, I will complete all the things. Okay. So I'm just giving you the rough idea of how or what I will do. Okay. So after that, we will check for the components that, okay. So for each one, we will check that if it is good or not, or if it is complete or not. Okay. If it is complete or not. So if, for example, complete, so we will add that value, right? So if is complete or is complete, and we will add the value of our total components. Okay. Total components. And in the end, we will simply return our total components. Okay. So this is how our structure would look like. So now let's start to fill our code. So first we will start with our adjacency list. Okay. For that, either you can create a list. Okay. So for the graph, or I just simply take, it's just my habit that, okay, I will take the default dictionary. You can take the 2D array. So it's completely fine with that. I will just simply take this. And after that, as we discussed, we will take from U to V, okay, in our edges. We will simply add the values of U dot append V, means the value from V to U and U to V. Okay. So this is our adjacency list done. So, okay, the first part is done. Now let's fill up the BFS function. Okay. So for BFS, we need couple of things. We need, if you remember, we need visited array. Okay. So I'll just add some of the things here, variable. So we have visited or seen, right? This can also be an array, or just I'll simply use array so that you can understand that. Okay. I'll take 0, it means that it is not visited, or you can take a Boolean one, whatever you like. And yeah, I think this is all. We only need visited array. Okay. Now we will start filling our BFS. So to fill the BFS, if you remember, we need a component that it will return. Okay. So currently our component would be empty. So we will start with our queue. Okay. So in the starting, our queue will have only one element. Okay. So we can either use this one, DQ, and we will add the node. You can also use a simple this. Okay. Whatever you like. I use DQ because it's, I think, a bit fast. So now in the BFS, if we are throwing up any element or any node, right? So it means that, okay, we are working on it. So this is now visited. Okay. So our current node would be visited. Okay. Now after that, we will iterate through our queue. Okay. So we will check that, okay, if our current element, how we will get the current element, because we have to pop the element. Okay. So we have to get it from the queue. Okay. After that, we will add that in our component because we got the value. So we will add that in our component, append current. Okay. So that way we will add that in our component that we are gonna return. Okay. So now we have to traverse to our neighbors also. Okay. So for neighbor in our graph, so this way it will give us these values, right? This one, 2 0 0 2. So this is our all neighbors. Okay. So this is the current. So 0 is the current one right now, right? And this all are would be neighbors. So this neighbor, and because we are running a loop, so it will iterate through each neighbor. Okay. I hope you understand that. Now we will iterate through our neighbor, but before that, we don't want to visit our neighbor again and again. So we will check that, okay, if we haven't visited the node, that is our neighbor node, then we will visit it. Okay. So whenever we visit it, we will add that in our queue. Okay. And we will say that, okay, now we have visited this, right? So this is how our BFS will look like. See, this is not that difficult. Just you have to understand how these things are working, right? The dry run and stuff like that. So I'll hopefully make a video of this one, BFS and DFS traversals. So that way you can understand better. Okay, for now, just bear with me, or you can just study it from other sources, or there are many sources. So you can use that. So this is the BFS part. Okay. So now the third part was to iterate. Okay. Now to iterate, we have to find this again that, okay, we are traversing through our indexes, the ranges, or the vertices. Okay. So for 0, we send that to a BFS. So that give us 0, 1, 2. Okay. But in the vertex, we have 1 now. Okay. But we have already visited that. We don't need that right now. So that way, we will check that, okay, if we haven't visited right now the current vertex, then please visit it. This will all go inside that, right? And after that, we found the components in our BFS that, okay, we haven't visited that. Give me the components of that particular component, the values, right? Then we will check that, okay, if is it is completed, we will simply first say that, okay, it is not completed. After that, we will check for the conditions. If you remember the condition was we have to check that, okay, this length is equal to n minus 1. If that's not the case, we have to simply come out of it. Okay. I hope you remember that. For that, we will first traverse our components. So for node in component, right? So we will say that, okay, if our now comes to the condition part. So now if length of this, so now this is our component right now. This is our node. So we'll check that, okay. So for this, the values, so the graph of 5 will give us this adjacency list. Okay. So this graph 3 will give us this adjacency list, right? Same way, this graph 2 would give us this adjacency list. Okay. So this length, we will check that, okay, for our graph in the node. If it is not equal to our length of component, n minus 1, if you remember, okay, n minus 1, then simply come out of it. So is complete would be false right now. Never mind. Okay, we will break out of it because it is not the perfect one, right? Sorry, we have to use the true one because we are using the false one here. So if it is not the case, then we will obviously break out of it and the value would be false. Otherwise, it would be true if we don't get into this condition. Okay, so it depends on you that how you want to do it, but I hope you're understanding that. Okay, so I think this is all. So let's just check if I have missed something. Of course, was there a total components? Okay, have I not? I defined it. Okay, anyways, I will define it here. Total components. This is accepted and it's pretty efficient. And I think this is the coding part of it. I hope you have understand that, right? Now talking about the time complexity. So usually this BFS, it takes we go of V plus E, like the vertices and the edges time complexity, and we are not doing any additional thing here. So I think that would be the time complexity of it, right? And also the space complexity would be we are just storing the adjacency list. So I think that requires the same big O of V plus E, right? So I think this is the coding and intuition part of it. And I hope you understood that. So if you have any doubt or any questions, you can simply drop that in the comment section. And yeah, that's it for the video. Thank you for your time. So have a nice day. I'll see you in the next one. Bye bye.